All right. If you have a notebook or you're taking notes on something or somewhere, you want to have that available. There will be some new kind of vocabulary terms that we haven't used before. So you might want to be able to document those. Otherwise, obviously, everything will be posted to the live class for resources. All right, so it is Thursday, November 19th, 2020. Today, we're going to be looking at two-way tables, the general addition rule, and Venn diagrams. And we'll also look at another way of creating a sample space at the end of the presentation. All right, so two-way tables and probability. When trying to determine probabilities involving two events, a two-way table can be used to display the sample space so the probability calculations are easier. This can be very useful. For example, the college statistics class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on two variables, gender, whether a student had their ears pierced. These are categorical variables, as a reminder, for all 178 students in the class. The two-way table displays their data. Ta-da. Here's our two-way table. Across the top, we have male or female for the gender. And then the rows are pierced ears, yes or no. All right. So this is our two-way table. We have our marginal distributions along the bottom and on the right-hand side. And then we have our counts for each thing. There's 19 males with their ears pierced, 84 females with their ears pierced, 71 males that do not have their ears pierced, and 4 females with no ear piercings. So we have all this data. We've looked at these type of two-way tables before with categorical data. All right, so let's answer some questions using our two-way table and probabilities. So before we start, we're going to define two events. All right. Oh, hey, you're not supposed to go there. What happened? No. Who's doing this? Dang it. 1 second. The little pen thing is not cooperating. There we go. All right, take two. All right, so we're gonna name two events. Event A will be that the gender is male. Event B will be pierced ears. Right, identifying these two things as events and giving them labeled A and B allows me to more easily use notation and answer these questions. So question A, suppose we choose a student at random, find the probability that the student has pierced ears. So we're looking for the probability of event B, pierced ears. So probability of event B, we're going to look at pierced ears, yes, total, 103. We're not considering gender in this case, we're just asking probability that the student chosen has pierced ears regardless of gender. Okay, so that will be 103 out of 178. Again, we'll just leave it as a fraction. We don't gotta do nothing with it. It's perfectly fine that way. 103 out of 178. Part B is now, is male and has pierced ears. So I'm going to look at male. I'm looking in this column. And yes, pierced ears. There are 19 males in this course, in this AP, theoretical AP stats, or stats course, who have pierced ears. And that's what this is asking, probability of A and B. Both things must happen to be counted. We have 19 males with pierced ears. The probability is 19 out of 178. Do you guys have any questions so far? Excuse me.
Can you describe the difference with and or again? Because I kind of forgot.
Yes, I can. And there'll be several other examples of that today, so this is a good thing to stress. So, and within probability and also in other fields of math, and is exclusive, meaning everything attached with an and has to occur to be counted. So we must have the event male, being male and having pierced ears. Both of those things have to occur for that outcome to be counted. We have 19 outcomes that were male and pierced ears. Part C here says is male or has pierced ears. That's P, A, or B. So either of these two things can occur to be counted. So that means we count all the males, because it's is male is one event, and we count anyone with pierced ears. So we look at this row and this column, right? We have a total of 90 and 103. We're counting everything that is male or has pierced ears. They all count. Now, we do have to be careful, and I'll explain this. I don't like my P. So we do 103 plus 90. That's a total of 193. How many students are in this class?
178.
178.
Yeah, there's only 178. I can't have an out. I'm sorry, what?
I said jinx because we both said it at the same time.
Yep. I can't have 193. I can't have, a probability greater than 1, right? Probability has to be between 0 and 1. So this isn't working. Can anyone see what happened to make it not work? Yes, Carrie, perfect. You counted male with pierced ears twice. They were counted when we counted up the yes pierced ears, and they were counted again when we counted the amount of males. This guy right here is the problem. We counted this twice. All right, so we have to make an adjustment. We have to fix that. We only want to count it once, so we subtract one counting of it. Oh, nice. I can't. I hate mistakes. There we go. Get rid of that guy. Put in the actual correct number. A 9. 193 minus 19. And we get 174. Excellent. Now, this makes sense. This is less than 1, which works. It could also be gotten by counting just the separate possible events. There's essentially four possible events, so to say, or combinations. We can have male with pierced ear, male with no pierced ear, female pierced, female not pierced. There's 4 of those like combinations. 3 of them account for P of A or B. If I add 71 plus 19 plus 84, I'll get 174. All right. As you get larger data sets, though, it becomes more difficult to do those types of things. So you want to use a rule, which comes next. But again, this probability is 174 out of 178. We could also see this as the only lonely number left out are the 4 people who are not male and do not have pierced ears. or the complement of this scenario. So, did that answer the question about the difference between and or? I don't remember who asked specifically, otherwise I would ask them, but I just want to make sure I've answered that question. Yes, all right, thank you, Antonio. All right, so now, we've seen how we can use this two-way table. It very easily allows us to pick out the numbers we need to write our probabilities. Very nice. This leads us to the next thing. So again, this is the illustration, another version of what we just talked about, where the outcomes are double counted right here. All right, the 19 was counted twice. So to account for that, to make sure we don't double count events, we have the general addition rule for two events. If A and B are any two events resulting from some chance process, then probability of A or B equals the probability of A plus the probability of B minus the probability of A and B, which is exactly what we did here. We added them and then subtracted the and, the 19. All right. So then one little note here, the addition rule for mutually exclusive events, which we saw on Tuesday, which said if two events A and B are mutually exclusive, then the probability of P A or B is equal to P of A plus P of B, is just a special case of the general addition rule for two events. When events A and B are disjoint or mutually exclusive, then the probability of A and B equals 0. And you are left with P of A plus P of B. Right? This last term here is just gone because it's minus 0. It doesn't change anything. So if you're going to commit one of these things to memory, you want this one because it always works, whether or not the events are disjoint. Okay. Does anyone have any questions or anything I can clarify? Okay. Does anyone need a moment to write anything down from this slide? Please raise your hand. Right. All right. Let's go. There we go. So now, Venn diagrams. Two-way tables are one way to illustrate the sample space of a chance process involving two events. Another way is to use Venn diagrams. Venn diagrams are used in other branches of mathematics, set theory to name one. Some standard notation and vocabulary have been developed because of this. Set theory is a major thing within what's called pure mathematics, which is more theoretical math, which is what I had to study in college. So we have the complement. This is the term that we saw on Tuesday. If A is an event, then the outcomes not in A are denoted A complement. Right? A superscript C. Superscript is like the little, where you would put like an exponent. Right? And we can illustrate this using a simple Venn diagram, where the box here represents the entirety of the sample space. We have event A is the circle. Everything outside of our circle is not in A and is therefore A complement. This is almost like a visual representation of the definition. Can you raise your hand if you are writing this down or copying the picture? Excellent. Next, we have mutually exclusive or disjoint. Again, this is something we saw on Tuesday's class. If A and B are two events with no outcomes in common, then they are mutually exclusive or disjoint. In the illustration, the events do not overlap. We have event A, event B. The circles don't cross each other, right? Which means they are disjoint. They have no outcomes in common, right? The whole square here, or not square, rectangle, labeled S, is the entirety of the sample space. Right? So these are all the other outcomes outside of A and B. Nice thing with Venn diagrams is you can add more events, right? Just add more circles, right? And you can kind of do a quick accounting of all the overlaps or not overlaps and things like that very visually. Right now we're only considering two. And can you raise your hand if you are writing this down or drawing the picture and need more time? Excellent. All right, now this is a new one. This is intersection. If A and B are two events with some outcomes in common, then they have an intersection. This intersection is the event A and B. In the illustration, the shaded area represents the intersection. The corresponding notation is A intersect B. Right? This little like curve, so to say, represents and or intersection. So you can read this A and B or A intersect B. Okay, so this is a new notation. Again, if you'd like a minute to write these things down or finish writing them down or drawing the picture, raise your hand. Right. Next, And the last new term here is union. If A and B are two events in a sample space, the union is the outcomes of both events. This union is the event A or B. Right, so in here, everything within A and B is part of the union. In the illustration, the shaded area represents the union. The corresponding notation is A union B, or we can read it as A or B. Right? Think of it as like they call a marriage a union, right? What belongs to A now also belongs to B, and what belongs to B also belongs to A because they're in a union. Excuse me. And one more time. If you'd like some time to finish writing these down or drawing the picture, please raise that hand. Okay. So then, let's look at examples of using this stuff. So we're going to revisit the pierced ear data from earlier. Here it is. We're just missing the marginal distributions because we don't need them for this. And here's a Venn diagram showing the same events and the accompanying count. So now, first, we have the same two events highlighted. A is male. B has pierced ears. Those are our two events again. So first part here, A. How many things are in A and B? Male and has pierced ears. We did this one on the previous set of examples. We know that that is 19. Okay. So then the probability of A and B occurring will be 19 out of 178, as that was the total number of people in this survey. And again, we see that, we see right here on the two-way table, where we have that intersection of male and yes. And then in the Venn diagram, it's this green middle part here. Okay. These are the 19 outcomes that are shared between event A and event B. So now let's consider A intersection B complement. So we have event A, that's this whole thing here. Event A, 19 and 71, all the males. And B complement is everything not in B. So I need to have things that are not pierced ears. So in other words, this is saying the person selected is male and their ears are not pierced. And if we look at our two-way table, that is 71 here. That is the number of males who do not have pierced ears. We see that in the Venn diagram as this like Pac-Man section, so to say, of the yellow circle. Everything except those 19 shared outcomes. So we have 17 or 71 count here, which means the probability is 71 out of 178. there any questions on this so far, how we're putting these pieces together? All right. So then, let me ask you, what is a complement? What would be that event?
Female?
Yes. We could say not male or female, right? So a complement is referring to the female category, and B, which is has pierced ears. So E wants to know how many females have pierced ears. So that gives us this 84. Right? So this becomes easier, so to say, if we decipher what the code is, right? A complement intersects B sounds like a bunch of silliness, but if we consider what does A complement represent, it represents females. B represents pierced ears, so that this is actually asking us to count how many females have pierced ears. That's much easier to understand. We just need to decipher the code. So we get 84 here, which means the probability is 84 out of 178. Now the reason we have the notation, right, is to make writing about this easier. I just name the events at the top of the page, and then I just use the notation throughout. That writes a lot faster than having to write out what is the probability that a female has their ears pierced, when I can just write A complement intersect B. See? Mathematicians love their notation. So last one, or last pair, we're looking at, oh, what color do I want? There. Right. A complement and B complement. We already established A complement is female. What is B complement?
Females whose ears aren't pierced?
Yeah, so that's what G is asking. It says, how many females do not have pierced ears? Right? A complement and B complement. We're thinking of this just looking at the Venn diagram. It's like we want to know what outcomes are not part of A and are not part of C, or not part of B. Right? That leaves just these four here. Everything else is part of A and B. So we want what's not part of A and B, A complement and B complement. Again, if we're thinking of the deciphering it, it's female and no pierced ears. That's just these four. And we get the probability of 4 out of 178. Right. Is there anything I can clarify in here? Okay. Does anyone need a moment to write any of this down? Okay. So again, this will be available. The pictures of the slides and everything will be available in the live class resources. I'm going to end the slideshow here and go to our one last example of creating a sample space. Yeah. All right. So now this one's a little bit different, which is why I'm showing it here. And the section of the textbook that this stuff just should have been in, I didn't see it, so that's why I'm doing my own example here. So we need to create a sample space from a choice process where we're randomly selecting two, in this case, 2 things out of a set of 6. It could be 3 things out of a set of 7 or 2 things out of a set of 4. So we don't just have, It doesn't work the same as like a two-way table or a Venn diagram. We have to kind of create the sample space. So we're going to look at this context here. We have 6 friends: Allison, Bree, Chuck, Dan, Ella, and Francisco. And they're the finalists for a prize drawing. And the prize is 2 tickets to a concert. Woo. Excuse me. 2 of them will be selected at random as the winners. What are the chances that Bree and Francisco are selected? So if it was just, what are the chances one of them is selected, and they're all equally likely, it'd be 1 out of 6, right? But we're randomly selecting 2 people out of the 6, and we're asking about 2 specific people. So now we create all the possibilities. We need to have the outcome space. So I'm going to use the first letter of each person's name, which is why I used a different letter for each person's name to represent that person. And we're going to write out all the different combinations of pairs of winners, right? So we can have AB, AC, AD, AE, or AF. Then we move on to start with the letter B. We can have BC, BD, BE, or BF. Move on to letter C. We can have CD, CE, or CF, D, DE, or DF, and lastly, we have E, F, and after that, we have no more options. F has already been paired with everything. This sample space represents the idea that the order in which the names are selected doesn't matter. If this is a random drawing and A is selected first and then B, it's the same as if B was selected and then A. So the order in which the names are chosen doesn't matter. The case where the order matters comes later, right? So this represents all the possible combinations. So that means we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 possible outcomes that are all equally likely. Now, also the way, my strategy in which I wrote down the possible outcomes is consistent for me. I do it that way to make sure I don't forget anything. You can see that it kind of goes in descending order, like it gets smaller as I work through the examples. I know that each subsequent row has 1 less thing than the previous one. So eventually I run out, and I know I've covered everything. All right, so we have 15 possible equally likely outcomes. I want B and F, Bree and Francisco. That is this one. This is the only outcome that represents those 2 people being chosen. So there is a probability 1 out of 15. So the chances that Bree and Francisco are selected is 1 out of 15. Right. And we could do different combinations of like, what are the chances that is selected? Well, there's 5 possibilities, right? We can do different combinations of chances of things using the sample space. Any questions on the sample? Okay, so then, last thing here, go into our module. So, a few things here. So we have our live class resources. Those will be updated. The week 13 CYU is a multiple choice quiz. It is all multiple choice. There are 4 questions. Here's just some things that you should know. First question, you're going to use a relative frequency table where like having 0 callers waiting more than 8 minutes has a 0.181 probability of happening and so on. The numbers at the top of each row or each column represents the probability of that number of callers. You have to use your understanding of probability to answer that question. We have a two-way table question. Question 3 is like the example we just did. And question 4 is using our new notation and asking about mutually exclusive events. That's it. That's the entirety of the quiz. Excuse me. And then our discussion board. Standard deck of playing cards with jokers removed consists of 52 cards in 4 suits. Clubs, diamonds, hearts, and spades. Each suit has 13 cards with denominations. I messed up. Hold on. Let's just fix it so I don't forget. Ace takes the place of 1. Right. All right, now it's fixed. Denominations ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. The jack, queen, and king are referred to as face cards. Imagine that we shuffle the decks early and deal 1 card. Let's define events F, getting a face card, and H, getting a heart. And so when your first task is to make a two-way table. At the top of the two-way table, you could have the events, face card, not a face card. The rows could be labeled heart, not a heart. Then you fill in the numbers accordingly. Right? And then define the probability of having a face card and it being a heart, and explain why the probability of F or H is not equivalent to the probability of F plus probability of H. Then use the general addition rule to find P of F or H. And that's it. Any questions about the discussion board or quiz?
I'm confused on the notation.
On the discussion board, or the and or notation.
Yeah, the and the or and all that. Like where you were pulling. Like, can you like briefly re-explain it, please?
Mm-hmm. So, look here real quick. So we have our probability notation, which is probability parentheses event, so to say. And that just says determine the probability of the thing in the parentheses happening. We typically will name events using capital letters. So I can have A, B, event A, B, right, can be event B. Whatever these may be having to do, like in the discussion board, we'll have event F, face card, event H, heart, right? So then if I want the probability of A, I want to know what are the chances of this event occurring based on the total number of outcomes possible, right? We have like number of outcomes in A divided by number of total outcomes. Right? And P of B would be the same thing, just switch A for B. And then we have a complement. Right? And A complement is all outcomes not in A. All right. And so anything that's not part of event A, any outcome that's not part of event A is part of a complement. Right. Then the other new notation we have is intersection, which is this like arch and union. Yes, Fernando, go to work. Have a good day. All right. And union. So when I'm looking at A and B, this wants to know essentially the number of outcomes the events share. So the number of outcomes that happened in event A and also happened in event B. A union B, number of events or number of outcomes both events have in total. So essentially, the union is adding up all the outcomes between the two events. The intersection is only counting the outcomes that both events have in common.